Hey, welcome back to Coronavirus University. I thought I'd try to squeeze in one last short video about coordinates with respect to a basis or two different bases for either one or two different vector spaces and the matrix for the corresponding linear map. Okay, so suppose I've got a vector space V with a basis B and a vector space W with the basis, maybe I'll call it C. I'll try to use the calligraphic letters, and a linear map between them. So L is a linear map. Right? Here's a linear map. Okay. So this could be Rn and Rm, but it could also be something infinite dimensional. And if you like, you could even think of V, if you like, we talked about this in one of my sections, you think of V as the functions, okay, from B to the real numbers that are finitely supported, meaning they're non-zero only on a finite set. Okay? So non-zero on a finite set of vectors in B, of these basis vectors. So this is a basis for B, basis for W. Okay, so that's another way to think of a basis. It's of a vector space. You identify a vector as a linear combination, which is a finite sum of weighted sums of elements of the basis. But you can also think of the values of the function, okay, as the coefficients, as the weights. So the coordinates, if you like, with respect to the basis. That would be the functions. Okay, anyway, so this is a little bit abstract maybe, but suppose I have such a linear map. Well, then we can actually make a coordinate map. Okay, so there's a coordinate map with respect to the basis. Okay, so maybe I'll make that in red. There's the coordinate map. Okay, so the coordinate map goes down. Okay. In fact, it goes down to this. This is what the coordinate map gives you. So this is sort of like, you might think of this as if you like, the coordinates. Okay, the coordinate map is the coordinates with respect to the basis. And here again, I've got the coordinate map with respect to the basis. Okay, and if you like, you can think of this as these finite supported guys. So I'll just make some notation for that. RC. So this would be like Rn and Rm in the case where these are finite dimensional. Okay. And then there's a matrix. So a number of C times number of B matrix. Okay, so there's some matrix L. I'll use L for that, but I'll say a little bit more about the notation in a minute. So this L lives in here. L lives in L is if you like in R C by B. So it's going to be a finitely supported matrix. Okay. There's only finitely many non-zero entries. Again, if these are finite dimensional, everything here is finite, and that's good. Okay. So, in fact, I might want to reference the basis here, and sometimes I use this notation. I'll put C and B here, and the book uses some similar notation. Just to emphasize that I'm going from B to C, here I've got a vector space with basis B, here I've got a vector space basis C. I get a map like that. I got a map here, and then I get a corresponding matrix here. And this matrix has all the information about the map. So what is this matrix? So what is this matrix of the linear map? Okay. Well, I'll write the finite case down here. Okay, so technically I need an ordered basis, by the way, to make sense of the matrix. So maybe I'll put ordered basis here. So I need to be able to order it in order to actually define the map, this coordinate map. Okay. So what you simply do is you apply L. So I order the basis. So maybe my B, right, is somehow ordered. B1, B2, whatever. Okay, somehow ordered. Okay, so I might need a countable basis actually to write it as actual matrix with entries. So, but I'll let you think about it. You could have like a continuous matrix in general. It'd be kind of fun to understand what that means. Okay, but I take this ordered basis, right, and I take L of B1, L of B2, and so forth. And then so that's an element, right? I take a B in here, right? These B's live in here. And then L of B lives over here. It's a linear map. Lives here. So these are here. And I simply take the coordinates with respect to the basis C here. And those become the columns of the matrix. Okay, so I go through that. And this gives me, it gives me a matrix, as I said, in the number of elements in C and the number of elements in B, that product there. So this is the matrix. Okay, and let me just give you one special example. Okay, if I take V to be equal to W, so V to V, and I take just the identity linear map, just the sensitivity vector itself, but I have two different bases. Maybe I've got a basis B and a basis C, and I take coordinates with respect to those. So now this gives me R number of B. This gives me R, there's two different bases, so number of B equals number of C. Okay, so that I could put that C or B. Okay. And now I get if you like, a square matrix. Again, finite if everything is finite, which is the identity map, or 1. Maybe let's call it 1. It's the map that's equivalent to just multiplying by the scalar 1. So the identity map. Between these two bases, right? So this is the notation would be like this. The arrow going that way. So this is the so-called change of basis matrix. And you'll find this discussed a little bit in chapter 4. And just to think a little bit, you might think about what happens if I continue the diagram. So to think about, what if I go VW, suppose I have another linear map, M from W to X, and maybe this has a basis D, and then you get some kind of additional coordinate map here, coordinates with respect to D. That'll give you a vector in R to the D, so finally supported if you like, and a corresponding matrix here for this linear map. And you might ask yourself, how does the composition, which is a linear map, namely M after L, right? What is the matrix M after L for the with respect to the basis, starting with B, ending with D? What's the matrix for that composition? Well, it's the product of these two matrices. So I'll let you figure out how that works. Okay, so that's all I wanted to say. It's a little bit abstract, but you might sort that out, and it could be fun to understand that a little more deeply. I know one of my students, who's now a math professor learned that from me about 40 years ago, so you might study that too.